this is a last minute video where I want to give you some information about the final and also cover a little bit of nuclear chemistry because there's going to be a question, and since we have not really had time to cover that, just wanted to give you the basic information that you need. So what are you allowed to use to do the exam? So it's a this is not going to be open notes, right? So all you can use is your calculator, basically, in scrum paper. Any type of calculators, I don't care about that, right? I'm not even there to check. The cover page has been provided on Canvas, so you know, if you have a possibility to print it, that's kind of the more convenient thing. It contains all the equations that you're supposed, you know, to need, and some constants. So we're going to go over that. This is about checking what you have actually learned during this year, and not how good you are at looking stuff up on Google or on the internet. So you can't use any Google, you cannot communicate to your friends and schoolmates, no check, no Coursera, whatever, you name it. Now, this is all based on a reciprocal, you know, trust, on reciprocal trust. I'm not there. No matter how much I try to set up things in a complicated way, there's no way on earth I can really prevent you from cheating. To make it less desirable as possible, I've tried to reduce the anxiety associated with this exam by, so it's going to be 40 questions. You will have all the time you need, and I will give you more details on Canvas. If some people cheat, they are just penalizing the schoolmates that are more honest or maybe have less resources, and that's really not how, as a team, we've been trying to work so far. So as I said, I will give you more detail on Canvas, just because scripta manent and verba volant. Let's say there is more privacy there. So what equation are you given? It's important that you are able to identify what the equation is and when to use it, right? So you're going to see this equation. This is Arrhenius in the 2 points form. So for temperature, what's the effect of changing the temperature from T1 to T2 to the kinetic constants K1 and K2? So this is Arrhenius. What are the things that you can get tricked? Let's say where you can do a mistake here. First of all, let me get the pointer. Be careful with R. You need to pick the correct value of R, that is the one that has joules for the work part. So it's going to be 8.314. Don't use the other one. Because there are joules, you need to be careful if you are entering AEA, activation energy, that is typically given in kilojoules, but you have to transform into joules. Otherwise, there is a discrepancy in the unit in this part. So because you have joules here, you need joules here. So if it's kilojoules, you need to multiply by 1000. Temperature. The temperature needs to be in Kelvin. Typically, they are given in Celsius. The value would be, because you are subtracting the reciprocal, and the conversion Kelvin Celsius is obtained by summing, not by dividing or multiplying, you are going to have a completely different and unrelated number. The other thing is the correct pairing. So no matter if what reaction you have, no matter if it's endothermic or exothermic, an increase in temperature will always increase the speed of the reaction. So T2 is the larger temperature, K2 is the larger value of K. This equation is the Anderson-Hasselbalch equation to calculate the pH of a buffer solution. So I'm going in the next slide to refresh how to do pH calculation. So be careful, there is a logarithm on base 10, right? So this is a decimal logarithm, not a natural logarithm. This is the base and this is the acid. So on top you have the base, that is the formula that is missing one hydrogen respect to the other one. You need to be able to know well what's a buffer, right? So a buffer is going to be a mixture of two substances. So in order to have the buffer, you need to have two substances, a weak acid and its conjugated base, or a weak base and its conjugated acid. So they have to be conjugated and they have to be weak. You cannot make a buffer with hydrochloric acid and sodium chloride, because hydrochloric acid is strong. Okay, I'm feeling I should tell you something else. But this is the, there's a parenthesis missing. This is the Heisenberg equation to calculate the energy that is released or absorbed, depending which direction you're going with the electron, if an electron is transitioning in an hydrogen atom. So this kind of refers to the Bohr model. Now, more than actually, chances are that you may not necessarily have to use it to do the math, but just to make sense of what's happening. Now, as a general rule, if the electron is going from a lower level, so n is the first quantum number, the energy level, so it's going to be 1, 2, 3, 4. 1 being closest to the nucleus. If you have a larger number, the larger the number, the farther away from the nucleus. So in general, if the electron is going from level 1 to a higher level, is going up, so it's going, he needs energy to do that, to jump up. It's like going up the stairs. It's a workout, right? So it will be an endothermic process, and it will happen by absorption of energy. Maybe if you're lucky, they don't ask you exactly how much energy. They may just ask you to make a qualitative estimate, let's say. So which one is larger, which one is bigger? In which case, the larger is the difference between two energetic levels, the more energy is needed. So in other words, it takes more energy to go from level 1 to level 5 than it would take to go from level 1 to level 2. For the same reason, it's much harder to go on foot without taking the elevator all the way to the 5th floor. Is going to make you more tired than if you're going only to the 1st floor. Right? The opposite process, so if an electron is moving from a higher n to a lower n, so it's going downhill, that's going to be easy. That's going to be exothermic, right? So, and the energy is given off, typically in light, and the larger is the difference in the two levels, the larger is going to be the energy that's given off. So maybe if you're lucky, just by giving two values of n and what's the initial point and what's the arrival point, you don't have to do the math. You can just guess, which one has the highest energy or which one has the lowest energy. So pH calculation, you have basically three possible scenarios. You need to calculate the pH for a solution of a strong acid or a strong base. Or you have to calculate the pH for a solution of a weak acid or a weak base, or you have to calculate the pH for a buffer. Okay, so first thing you want to ask yourself, what's in this solution, in this problem? Is it just one thing, or are two? If there are two, is it a buffer? So it has to be a conjugated pair, and it has to be weak. But if there is only one thing, only one substance, then you need to ask yourself, is it an acid or is it a base? And you should be able to do that, right? If you're not able to do that, maybe you're not ready for the next class. So once you have figured out it, let's say it's an acid. Is it weak or is it strong, right? So the strong are those 6 that you need to memorize. If it's strong, you're lucky because that's the easiest calculation, because the pH, by definition, is minus the concentration of the H+. If it's a strong acid, the concentration of the H+ is identical to the concentration of the HA, because it's dissociated 100%. So you just plug that in the logarithm formula. If it's a strong base, it can get a little bit more complicated. There is more space for a mistake. So let's say, so first of all, strong bases are all hydroxide from group 1 and group 2. So here I use Me as symbol for metal from group 1 or group 2. So Me could be sodium, potassium, calcium. And then you have an N because if it's group 1, like sodium hydroxide, you have only one hydroxide ion. But if you are from group 2, you have two of those, right? So let's say that you have a solution that is 0.1 molar and is calcium hydroxide. And you need to calculate the pH, right? So first of all, you are going to get as first step the pOH because you have a base, so you're going to calculate the concentration of the OH minus. So what's the concentration of the OH minus? Because it's a strong base, it's going to be equal to some extent, up to a point, to the concentration of the base itself. So if the calcium hydroxide is 0.1 molar, what's the concentration of the H minus? Well, it's going to be 0.2 molar because you have two, right, ions per each unit, so it's going to be 0.2. So the first place where you can do a mistake is calculate the logarithm of 0.1 instead of the logarithm of 0.2, and you bet that that's going to be one of the possible wrong answers. There is a difference between an acid and a base. If I have a diprotic acid, that pretty much of all the strong acid, the only one that has two hydrogen is sulfuric, but it's strong only for the first dissociation. By the time you get the second dissociation, it's quite weak. So the pH is affected only from the first. Is affected only by the first dissociation, so you don't have to make any adjustment. But calcium hydroxide, barium hydroxide, strontium hydroxide, those are ionic, so it's all separated. So you get exactly twice as many OH minus as unit of calcium hydroxide. Okay. So once you have the concentration of the OH minus, you need to calculate minus the logarithm of this. Now this is going to be the pOH. No, you don't have yet the pH, but you can bet that one of the wrong answer in the multiple choice is going to be that number. So to get the actual pH, you need to go minus the logarithm of 0.2. So let's see what comes up with. Okay, so it's going to be 0.67. So let's say the pOH is going to be equal to 0.70. Let's round up. Now I have let me think. No, I have one Cfig. There is no 0 because only one Cfig. So it doesn't matter. You don't have to worry about this. You have a multiple choice. So you bet that one of the wrong answer is going to be 0.7. But you should not fall for that because this is a base. The pH should be basic. The pH is going to be basic for any value larger than 7. So 0.7 as an answer to this question would not make any sense. You need to go 14 minus 0.7 and you get 13.3. That's a very basic pH. That makes sense. Okay. Weak acid. For the weak acid, you need to remember that the Ka that is going to be given, right, is going to be the concentration of the H plus, the concentration of the A minus. Now, I'm assuming you remember that, but let's just not give anything for granted. Like, this is the equilibrium for the dissociation of the weak acid, generic HA. Okay, so in here you put H, the concentration of the HA. Now this should be all concentration at equilibrium, right? So if the weak acid is the only thing you have there, you don't have common ions or anything, these two concentrations are identical. So this becomes the same number, X, let's call it X. This is X squared. Now at the bottom, we should put the concentration of the HA at equilibrium. That's going to be less than the initial concentration. So it should be the initial concentration minus X. But you can definitely go for the simplification, you know, the 5% rule thing. So assume that X is so small and that when you do the subtraction, pretty much this is going to be almost as identical to HA. Okay. If you remember, the rule of thumb is that that's okay as long as HA, the initial concentration, is large enough and Ka is small enough. And that means this inequality to be happening. Okay. So that's 400 is really written awfully, but it's not hard to write with the mouse. So if the concentration of the acid is at least 400 times bigger than the value of the Ka, you should be fine doing this simplification. Just go for it. Okay. And then once you have the H plus, that would be X, you can calculate the pH. For the base is the same reasoning, except you end up with the concentration of the OH minus, so you calculate the decimal logarithm, you get the POH, and then you need to calculate the pH as 14 minus that. I didn't want to do that, I want it to be yellow. Okay. Then, if it's a buffer, it's the Anderson-Hasselbalch bucket that we've seen in the other slide. More equations. So you have the Nernst equation, where this is the Nernst equation is used to calculate the potential of a cell if you are not in standard condition. This is the potential in non-standard condition. This is the potential in standard condition. It's the one that you calculate simply by going cathode minus anode. R is the gas constant, T is the temperature in Kelvin, N is the number of electrons exchanged in the balance equation, F is the Faraday constant, Q is the quotient of the reaction. That would be the concentration of the products minus the concentration of the reactants. You may be not at standard condition, either because, let's use a different color, let's use blue, the temperature is off, is not 25 Celsius, is something else. More often is because of this. First law, thermodynamic. So the variation in internal energy of a system can be calculated as the sum between the heat exchange and the work exchanged. We have a bunch of equations for delta G that are given. So the first one is determining the spontaneity of an equation, of a reaction, by combining the information about the reaction being exo or endothermic, that's this first term here, to the information about the system, what's happening to the system in terms of entropy. Now, you have two possible scenarios for this. You might be given numbers, right? So you may know the delta H of the reaction. For example, they tell you the reaction is exothermic and is given off 320 joules per mole. So they actually give you the number, and then you get the number for delta S, and then you need the temperature, and then you put together all those numbers. Or it may be more subtle, like they don't tell you, they don't give you numbers. They just tell you, for example, that the reaction is exo or endothermic. It's unlikely that they actually tell you that explicitly. They may give you information so that you're able to infer that the reaction is exo or endothermic. For example, it may be a change of state, so you're supposed to know that, let's say, melting ice is endothermic as opposed to condensation of vapor that is exothermic. So that type of thing, or it's something in burning that's exothermic. So it could be a situation where, you know, it's kind of a known fact that the reaction is exo or endothermic, or you could have one of those energy diagram, the one that looks like that, you know, where you have this, and you know that, let's say this would be exothermic, for example. So these are the reactants, and these are the product. Right. So if you have the graph, you know which one is which, and so forth. So somehow you have a way to figure out not the value but the sign of delta H. And then if the reaction is written, you know how to determine delta S, because these are those exercises where we were looking at a reaction and determining if this delta S is the delta S of the system. So you just need the reaction, see if it gets in more order. So for example, so if the products show more order, then delta S is negative, S is going down. So you want to look for example, is it going from solid to liquid to gas? Do you have more molecule, you know, on the product side, on the reagent side? So have a look at that, right? Because that also allow you to get the sign. Now, if you don't have numbers, but you just have signs, so if you know that their reaction is as a negative delta H and as a positive delta S, you can infer in which condition would be spontaneous, because if delta H is negative and delta S is positive, because of this minus sign, okay, you're going to have that what's on this side is going to be negative, because so delta S is positive, here you have a minus, you put together this information and you get a minus. If this is also a minus, then delta G is going to be a minus. So that would let you allow you to say, for example, that the reaction is spontaneous at any temperature, right? So you can have a problem either where you have to do the math, or where you have to kind of reason in terms of qualitatively. If it's a particularly hard problem, then you may have to actually, you may be given the delta H of formation of all the species, the delta S, the S of formation, the S of formation of all the species, and then you have to calculate delta H and delta S, and then you have to plug them in the formula. So that would be the longest scenario. In the lower part here, you have the relationship between delta G and the equilibrium constant. So this equation is used to convert between delta G. So if delta G is negative, the reaction is spontaneous, in which case K would be big because you would have a lot of products and so forth. The one at the bottom is the one that correlates delta G with the cell potential. So, you know, remember that the cell potential, if the reaction is spontaneous, so it's a galvanic cell, so E is positive and delta G is negative. But if you have to do the math, that's the equation. So you are given the integrated rate law. Now, I don't remember if in that particular cover you are also told this is 0. So you see here you have not just the equation, but is also labeled. So you know that this is the integrated rate law for order 0, and this is the integrated rate law for order 2. So, but you have the cover, so you can check that. Even if this part is not there, they are in order from small to big, so it's not rocket science. The one in the middle is especially important because first-order kinetics correspond to the kinetics of radioactive decay, right? So you may get a question of that, and we will see eventually. So there is a bunch of constants. Be very careful with R, right? Because you have two. I wanted the highlighter actually. Okay. So you have this and you have this. So you need to be used to use the right one at the right moment. So the part that I didn't cover in class was nuclear reaction. We are going to be very, very basic. Okay, just what you need to for the problems. So in general, there are a variety of nuclear reaction. A nuclear reaction is any process that changes the composition of the nucleus. So for 2 semesters, you'll be just focusing on reaction where there was transfer of electrons, loss of electrons, acquisition of electrons, but the nucleus was never touched. While in nuclear reaction, instead, the nucleus is interested, so you can have loss, you know, the number of the neutrons, the number of the protons can go up, can go down, and this means that the atomic mass is going to change, so you're going to have a different isotope, but you can also end up with different elements, because if you're changing the number of protons, you have different elements between the left and the right of the equation. So that means that the process of balancing this equation is a bit different. So we have two types of nuclear reaction. More often than so, if you're talking of nuclear reaction, radioactive decay should not be included. It's kind of a thing on its own. So nuclear reaction, you don't really have to worry about it because there's going to be nothing in the final, but just to contextualize. So we have fission, where fixing, you know, may remind you of a concept of stitching things together, but actually means that it breaks. So you have a large nucleus that's unstable and is going to break into smaller nuclei. Fusion is the process of combining two small nuclei in a slightly larger one, in a new element, and that's what provides the energy in stars. So as I said, we don't really have to worry too much, because mostly we're going to, the only thing you need to worry about is radioactive decay. Okay, so when you have a nuclear reaction, it's not so much about balancing the element, because elements may be different from products and reactants, but it's about balancing the subatomic particles, because it's still true that nothing is going to be created or destroyed. So you're going to have your reactants, for which you will have to specify not just the formula, but typically they are atoms, so you have to also add the atomic mass and the atomic number, right? And the same for the product. So here you can see let me get pointed. Here you see the example of carbon, right? So just to to refresh how to write the isotope. So remember it like that the larger number is the one on top. So 6 is the atomic number that to some extent is redundant, because every atom of carbon has 6 protons, and every atom that has 6 protons is carbon. So just by putting the symbol, that should be implied that there are 6 protons. But because we need to balance protons, neutrons, and electrons, it's convenient to have it written down, because it helps us doing the math. 12 is the mass of the carbon. So that's a specific isotope in which, besides 6 protons, there are 6 neutrons, and so the total is 12. You can have carbon 13 when there would be an extra neutron, so that would be a different isotope. Okay, so let's keep as a reference the isotope of carbon 12, and then we compare everything to that. So the problem is, how do I write subatomic particles, right? Because for carbon I write a 12 in the top corner. That's the mass. So I can use a number to indicate the mass of these subatomic particles. Right, we have done the simplification that protons and neutrons have more or less the same mass. That's 1 in if measured in AMU. Although the neutron is a bit heavier, but it's a very small difference, so we can just simplify and assume that they are identical. And the electrons, it does have a mass, it's just so small that we simplify by saying, well, let's pretend it's 0. It's like putting a feather on the back of an elephant, right? The feather does have a weight, but if I'm just measuring elephants, comparing elephants, having a feather there or not is not going to make a difference. So the problem is, what do I write below? Because carbon, so that 6 is the atomic number, is the number of protons, but it doesn't really make sense if I'm writing a neutron or an electron. What number am I going to write? So in that position, it can be useful to think to that position as used to indicate the charge, basically. That's technically a little bit incorrect, but it just makes our life easier. So for an electron, therefore, we use the symbol E, the initial of the word, and then we put 0 on top because we assume, we simplify and we say that the mass is almost 0, is negligible. And then at the bottom we put the charge of the electron. That's a negative charge. So a proton is going to have a mass of 1 because that's our AMU, right? Correspond, and then is going to have a +1. So the plus, as usual, can be omitted. And then we have the neutron that has no charge. So in that case we have a 0 at the bottom, and at the top we have a 1. So remember that you don't really have to write them, it's a multiple choice, so as long as you can identify them, you're good. Now the interesting thing is that, as I told you, actually we simplify and we say that both neutron and proton have a mass of 1 AMU, but the neutron is slightly heavier. The reason it's slightly heavier is that if you put together an electron and a proton, you get a neutron. And this is interesting because it shows you that there is a relationship between what's written on top, on the reagent side and on the product side, and what's written at the bottom. So on top you have 0 and 1. So if you sum them up, you get 1, and that's what you see here. So there has to be a consistency between the sum of all the masses before and after. And the same below here, you see that there is a -1 and a +1, and plus and -1 gives you 0. So there is also a nice correspondence. So this is a bit of a summary of like unusual things that you may see in a nuclear reaction. So so far you have been using the element symbols and then putting together elements to make molecules, but you've never seen this kind of stuff. So there are these alpha particles. Alpha particles correspond to helium. So helium in its most stable isotope has 2 protons and 2 neutrons, so the sum is 4. So it could also be written like that, right? So alpha and helium is pretty much the same thing. Beta particles are electrons. So why do we have to use a different name? But for one thing, when they identify them, they didn't know necessarily they were electrons. But beta particles in general is used when you want to indicate not just normal electrons, but electrons with a lot of energy that are going very, very, very fast. So the symbol could be either E or beta, of the letter beta. The positron is a particle that has the same mass of an electron, so pretty much 0, but the charge is positive. You know, positron emission tomography. So as much as it seems something odd, it is actually a pretty important practical application. Do you have to worry about this in this exam? No. The proton, right? So you see, I don't even highlight the positron. I highlight only the thing that you need to remember. The proton, okay, is enough. Neutron is enough. Gamma ray. So sometimes during a decay, there is an emission of gamma ray. Now, gamma ray is a type of an electromagnetic radiation. So it's not a particle. It's an electromagnetic radiation. So there are no numbers there. Those are really, really, they carry a lot of energy. They have a wavelength that's much smaller than, let's say, UV. So, and those are, you know, responsible for acute damage in the body when one is exposed to radiation. I don't know if you had a chance to see, I think it was on Netflix, there was this really cool documentary about Chernobyl. It was in several episodes, so it was going quite in depth, and it had very graphic representation of the damage, especially on the firefighters. So those damages would have been given by the gamma radiation. So if an atom is emitting gamma radiation during the decay, is not really changing its nature, is not changing what element it is or its mass, because emitting gamma ray does not correspond to losing protons or neutrons or electrons. Okay, so what type of decay there are? There are several, but the good news is you really have to remember only three. Okay, so alpha decay, beta decay, and gamma decay. Don't worry about the other two. So an alpha decay is an emission of an alpha particle, so an emission of 2 protons, 2 neutrons, of a little nucleus of helium. A beta decay is the emission of an electron with a lot of energy, and a gamma decay is the emission of gamma radiation. So what do you get as a result? If you have a gamma decay, you are not changing the number of protons nor the number of neutrons. So the element is going to be the same with the same mass. So you do not get, because of a gamma emission, you do not get a different isotope. With the beta decay, you're emitting electrons. Where are those electrons coming from? Those are not the electrons like valence electrons or so it's not, because normally you may think that when you lose an electron you become a positive ion. This is a different thing. That electron is coming from a neutron, right? So what's going to happen is that what was a neutron that here is represented by, let me get the pointer. See that there is a circle here around this gray little sphere. So I'm assuming that here the green spheres, let's hope that you are not colorblind, the green spheres, so for example like this one or this one, these are protons, right? Because that would be a neutron. Those are protons. So the green are protons, and the gray one are the neutrons, right? So the one circle here is a neutron. So this neutron is breaking down into a proton and an electron. The electron is shot out of the molecule. You see this little thing with the minus sign. The consequence is now that this atom, that's the product, it has the same mass because I have a missing neutron, but I've made a new proton, so they both pretty much are 1, so the mass is not changed, right? So the number at the top, the big number, is not changed. But I have now an extra proton, so I don't have the same element that I had before. Now I have an element that's one step ahead in the periodic table. Okay, for the alpha decay, you see they have circled here 2 green, 2 gray, so this is a nucleum of helium, so this is helium, And as a consequence, I have a lot of stuff missing. I have four heavy, four particles that are important for the mass that are missing. So my mass, the mass is down of 4 units. So A is going to be four units lower. The atomic number also has changed because I have missed 2 protons. So now I have gone 2 steps back in the periodic table, and I have a different element. Okay. So as I said, all you need to remember are these. Okay, let's see some example. This is a type of problem you can get. Write the product for these 3 decays. Now, keep in mind, what you're going to have is a multiple choice. So most of the reaction is going to be written. That's not the case here. Here I'm going to write everything, but that's just because it helps understanding. But in the exam, you have the majority of the reaction written, there's a blank, and then you have 4 options to fill the blank. Right? So it's going to be much easier than this. So I'm going to start by writing my reactant. I know it's americium, and I'm given the particular isotope, that particular isotope mass, so it's going to be 241. Then I look for americium on the periodic table. Again, you have a multiple choice, so you don't have to worry about that. And I found that is element number 95, so I know the atomic mass. Then I know that it's an alpha decay, so on the other, on the product side, I'm going to have helium that has a mass of 4 because there are 2 protons and 2 neutrons. So that you would have that on the test, and then you would have to figure out among 4 choices what to write on the reactant side. So how do we do that? Okay, we need to find the element that has. So what we want to do, let me get the pointer. We need to have a situation where these 2 numbers sum up, give me 241. So I have the 241, I have the 4. So what I have to do is 241 minus 4, 237. That's going to be the mass of my product. Then I have 95 as number of protons, right? And then I have 2 protons here, so I have 93 missing. So that means that the number of protons for my product is going to be 93. Then I go to the periodic table and look which element is 93. That you don't have to do because that would be one of the 4 choices, right? So basically what you have to do is pick among the 4 options the one that, when put in this position, allows you to have that the sum of 4 and 237 is 241, and the sum of 2 and 93 is 95. In this case, I have carbon 14 that undergoes beta decay. So here on this side, I have an electron with high speed. So I need to find an element that has the same, so the atomic mass of the element that's the product is going still to be 14, but the atomic number is going to be have to be 5, so that when I go 5 minus 1 gives me 6. It has to be 7, I'm sorry. It has to be 7, so that 7 minus 1 gives me 6. So that corresponds to nitrogen. So this time, so again, you have on the product side a different element. If you have a gamma decay, right, so you write your reactant, a gamma particle doesn't have any protons or any neutrons and any electrons, so you're not changing in any way neither the mass or the identity. So you're pretty much having the same thing. So that's way too simple. That's unlikely that we put this in the exam. You know, it would just be too easy, I guess. Another example, again, let's try to find the product here. So we want to have an element here that is x, right? I don't know what it is. So on top, 232 minus 4 is 228. So when I go 228 plus 4, I get 232. And then here I want 88, right? So when I go 88 plus 2, I get 90. So I need to go in the periodic table, figure out who is 88, and that's going to be radon. And so that's the solution, okay? Again, it's a multiple choice. The second type of problem that you can get about nuclear reaction is calculation of the amount left after a certain number of hours or seconds for a radioactive isotope. But that's actually, we have solved those type of problems in the kinetic units. So you know already how to do those. Basically, assume that if it's probably going to tell you that in the problem, but assume that the nuclear decay follows first order kinetics. So of the three integrated rate law, you need the one in the middle, the one with the logarithm. Why do you need an integrated rate law? Typically, these problems are asking you, they give you the kinetic, let me get the highlighter. They're giving you the value of k, so the kinetic constant, and then they want to know, how much you have left of the isotopes after a certain amount of time, and so forth. So ADT this is the concentration of A after this time has elapsed, while A0 is the concentration at the very beginning, so when right for time 0. So initial and final concentration. Some of these problems imply talk about carbon 14. So carbon 14 is an isotope of carbon. Most carbon atoms are 12, isotope 12. Carbon 14 is present in the air, so in the CO2 of the air, and in general in every thing that contains carbon on planet Earth, in an amount that reflects its amount in the atmosphere, and because it's formed in the upper layer of the atmosphere due to radiation coming from the sun. So it's present in a very low percentage. As long as an organism is alive, let's say, the amount of carbon stays constant over time, because even if it's decaying, but you're breathing new air, that CO2 is going to be incorporated in by the photosynthesis in the tree, and then you eat vegetables, so the amount is kept constant. But by the time an organism dies, then you will have a progressive lowering of the amount of carbon 14 due to decay. So if you take as a reference the ratio between carbon 12 and carbon 14, so the ratio between those two as a reference in a living organism equal to 1. If you go and check that ratio in a dead organism or anything that's made from organic materials, you get a lower percentage, right? So the percentage of C14 is going to go down in a way that is related to the number of years from the production from the moment that animal died, or if you're looking at an artifact that's made out of vegetables or animal, then it's going to be from the moment of the that plant was processed, or that skin, because certain manuscripts are on skin and so forth. So in this example, the problem is to determine the age of an artifact based on the fact that the amount of the ratio between carbon 14 and carbon 12 is only 79.5% respect to what you would find in a living plant or animal now. So it just bothers me. But I copied this from the book, but it's a scrap of paper, but it's not like they were using paper. This is stuff. So these are the most ancient manuscript with the scriptures, so from the Bible. They were found on the West Bank, and they are not written on paper because they didn't have paper at the time. They are considered between 300 BC and 100 Common Era. So they wouldn't be written on paper. It would be papyrus or parchment. Papyrus is vegetable in origin, and parchment is animal. I think it's made out of the skin of sheep or something like that. So being having an organic nature, you can date it. If you're trying to date dinosaur with carbon dating, it doesn't work because that's a mineral. It's a fossil. So you can assume that your initial amount is 100%, and the final amount is 79.5%. And so you can plug those in the first order integrated law that you can see here, right? So in this equation you need the k, the constant that's given in the problem, and is the units are years to the -1. And then you need to figure out how much you have at time t and how much you had at the beginning. So the beginning we take it as reference, so it's 100, and at time t we know that we have 79.5. So that's what was measured. That's a measurement. So we have 3 sig fig. So we can write this, we can plug them in. It's more convenient to take 1 and 0.79 as opposed to 179.5 because the logarithm of 1 then is 0. It doesn't change anything mathematically because when you bring this on the other side of the equal sign, it becomes minus. That means that the logarithm of 0.79 the logarithm of 0.795 minus the logarithm of 1 would become the logarithm of the ratio. And so the ratio is the same in this equation and in this. So it doesn't, I feel confident taking this one because it's just simpler. Because then logarithm of 1 is 0, it goes away. And then I solve, and because the constant was in years to the -1, I get the time in years. Now, this is a good example of use of sig fig because what the calculator gives you is this number here. That seems to imply that you're such a good carbon dater that you can even tell the month in which the papyrus was harvested, and that's obviously a bit ridiculous. So it's about using an integrated law for first order. Now, you may be lucky and get a problem like this. So you have iodine 131 that's used in as clinical application, is used to test the functioning of the thyroid, where most of the iodine in your body is concentrated. The thyroid is a gland in your neck that controls the metabolism and of your bodies, and it's relatively frequent to have issues either functioning too much or functioning not enough. But it's important that you have enough support of iodine in the diet for the thyroid to work properly, and especially during pregnancy it's important that the mother assumes enough iodine with the diet. Insufficient iodine in the diet during pregnancy leads to severe consequences on the baby, including severe mental retardation. That is the reason why most table salt is enriched with iodine. If you live close enough to the sea, you get naturally iodine with your diet, but you know, maybe not so much now, but there were areas where like isolated on the mountains or where iodine supply could have been an issue. So the half-life, it's short, relatively short, it's 8 days, we start with 40 grams. How much do we have left in 44 days? So the trick here is to figure out if the amount in time that you're supposed to do the calculation about is somehow in a simple ratio with the half-life, right? So if I divide 24 by 8, I get 3. So the amount of time is actually exactly 3 times the half-life. So that's going to make my life much easier, because the half-life is independent in a first-order kinetics, is independent from the initial amount of the substance. So every 8 days, I cut the concentration in half. And so if I have 3 half-lives, I just have to cut the concentration by 3 times. So I can go 40 grams divided 2 is going to be 20, and that's my first 8 days. And then divided 2 is 10, and at that point I have 16 days. And then I divide by 2 again, and it's 5, and at that point I get my 24 days. If you prefer a formula, you have a formula here. This is not given in the cover though. Okay. But if you have 3 fingers, you can do the math. Let's see an example that can be slightly trickier. Okay, so it looks like the other one. The problem is that when I go to calculate 3.7 divided 2.3, oh shoot, it's 161. It's not really a nice number, right? However, I can still avoid the calculator and reason myself out of this, because if the time would have been, instead of 3.7, would have been 2.3, well, that would have been one half-life, and therefore I would have had 2 times 10 to the 18 atoms left. For 4.6 years, there would have been 2 half-life, so I would have been left with only 1 times 10 to the 18 atoms. So 3.7 is kind of in between those two numbers, right? So I know that my correct answer needs to be less than 2, but more than 1. And that kind of cuts out immediately A and D, right? So for one thing, I'm left with only 2 choices. Now 3.7 is, now this is a logarithmic relationship, so it's not linear, so it's a bit risky, but doing this. But I may reason that 3.7 is much closer to 0.6 than it is, 3.7 is much closer to 4.6 than it is to 2.3. So I would expect that that number is not going to be 1.5, but it's going to be lower than 1.5, right? This is another example where the number of days that you are supposed to investigate, so 24 days, is a perfect multiple of the half-life, that's 4. So in 24 days I had 6 half-lives. So the problem becomes cutting in half 6 times my initial amount. In this case you get the final amount, you know that by the end you get 4. So you can go backwards and say, well, 4, so then it becomes 8, and then 16, and so forth. And then you get to 256 milligrams, or you can just apply the formula. But as I said, that formula is not given in the test. So that's pretty much all that there is about. Also remember that on your tube you also have all the you have access, let's say, to the videos that I use for the other class. And in the other class, while we were doing basically we covered kinetics and equilibrium. So you have, if you need to refresh that stuff, you have all the videos for that if you want. So you can just go exploring. And there is a part about the very first week. It was like let me think. It was solution properties, colligative properties. You don't have to worry about that. But you may, I mean, can be useful potentially to have a look at the kinetics one And the thermodynamic one, you have that though. Kinetics and equilibrium, acid-base equilibrium, and solubility product, that type of stuff. Okay, so that's all. Remember that you can get in touch with me anytime during the weekend, and I will answer you. If you are using my cell phone, text me, don't call me, because then I would see a number that I don't recognize, and I'm getting a lot of junk telephone, you know, robo calls, especially political one. I even got called by the state senator last week. I don't think he was aware of, I think it was better that I didn't answer. Let's put it like that. So, but you can answer anytime. You can call anytime, okay? So, ask me everything that's bothering you about the final, okay? Good luck.